Hello viewers, welcome to this video lecture series on analysis and design of algorithms. This session I'll be explaining you a sorting algorithm. The name of the sorting algorithm is comparison counting sort. With respect to the pseudocode, this algorithm is the simplest among all the sorting algorithms which you have studied earlier. But with respect to the time complexity and space complexity, I shall be telling you at the end of the session. Anytime for any algorithm, you are going to write the comment lines, then start writing the pseudocode. So this one, the very first one, we are saying it sorts an array by comparison counting. So the logic is comparison counting. What exactly is comparison counting? I shall explain in detail with an example. I'll trace the pseudocode and I'll show you all the steps that are being carried out in this comparison counting algorithm. The input is an array. Here we are taking an array A of n elements, and the output we are getting an array S of n elements in non-decreasing order. So all the elements will get sorted in the ascending order. The very first line of code here, if you see, for I equal to 0 to n minus 1, do count of I with 0. Count is an array here, and for each of the element, initially you are assigning the value 0. You are doing this for how many elements? 0 to n minus 1. Suppose if your n value is 6, then 0 to 5. For all these index values, your value for the count array will be 0 for every element. Then comes here the logic. It will start from here. See, this is one independent for loop for which you are going to carry out in the beginning. Then comes what? The for loop here, the outer for loop, then the inner for loop, and here you have the if else statement. So the logic ends here. See, in the beginning you have one for loop which is going to initialize the count array with 0 for all elements. At the end you have a for loop in which you are going to place the element in the array yes. Let us trace this pseudocode. I have taken one example here, 1, 2, 3, 4, 5, 6 elements. So it is like this. The count is an array here. Suppose if it is a 6 element, then I have to have how many? 6 positions in the array. So the same 6 positions I am just trying to place it here, fine, separately, to show how I am going to update the value. Whatever value gets inserted in this count is the index value in the array. So initially I'll put 0, 0, 0, 0 for all the elements. I'm assuming that all the elements are placed in the very first position in the array, which is not actually practically correct, but here to start with the pseudocode tracing, I'll assume like this. Update the values for the count. I'll leave some space here, and once again I'll start writing the elements here: 35, 81, 92, 15 and 41. Now the algorithm says that for I equal to 0 to n minus 2. So I variable is used to keep track of all the elements here. And there is one inner for loop j. So the j variable will keep track of the comparisons done for each of the element. As per the pseudocode, I has to operate from 0 to n minus 2 and j is I plus 1 to n minus 1, right? So we'll start now in the very first iteration or the first pass. Initially I equal to 0, fine. So I is pointing to the first element. I'll place the index values here for each of this, fine. So I is pointing to 0 now, and j will operate from I plus 1. I plus 1, I is 0, so 0 plus 1. So 0 plus 1 is 1, and j will operate from j equal to 1, j equal to 2, j equal to 3, j equal to 4 and j equal to 5. This is what I am trying to tell you. J is operating from 0 plus 1 to n minus 1. So n is 6, so here it will be what? 1 to 5. So 1 to 5, that is what I have written here, j equal to 1 to 5. Now j pointer is pointing here. The pseudocode says that you compare a of I with a of j. A of I is the first element in the array presently, and it is compared with what? A of j. A of j is the elements other than the first element. Whatever are the elements in the array, those elements we call it as a of j. So first time you have to compare like this, whether I is a of I is less than, or see, this is what is the a of I is less than a of j. So this is the comparison statement here in the pseudocode. If a of I is less than a of j, if it is true, then the value for the count variable for a of j will be incremented by 1. Otherwise the value for the count variable for a of I will be incremented. So whichever is higher, that respective count will get increased. Now first time we are comparing what? 68 with 35. Is it true? No, 35 is less, 68 is greater. We are comparing what? A of I less than A of j. A of A is 68. Is 68 less than 35? It is false. If it is false, the else part of the algorithm will get executed. Here count of I will get incremented by 1. Count of I is 0. So now this I value will get incremented by 1. So we will update the value. It is 1 now. So this was for j equal to 1. Next time j equal to 2. We'll compare whether 68 is less than 81. No, 81 is greater. So we have to increase what? The count for 81. Then we'll compare, and then j pointer will move. So j equal to 3. Whether 68 is less than 92. No, 92 is greater than 68. So we have to increment for 92 the count value. Next j equal to 4. Whether 68 is less than 15. No, 68 is greater than 15. So this time we have to increment the count for the 68 value. Next j becomes 5. So we'll compare now 68, whether 68 is less than 41. No, 68 only is greater than 41. So we'll increment the count for 68. Now the j loop gets completed. So it will go to the outer for loop and the value for I will be 1 now. It is pointing to the index 1, that is the element 35. So your I is pointing to 35 now and j is pointing to 81, which is j equal to 2. So in the second pass, I will operate from I equal to 1 and j equal to 2, j equal to 3, j equal to 4 and j equal to 5. So 4 elements are there. 1, 2, 3, 4. These 4 elements get compared with the first element in the array. First element in the array is 35. So start comparing. A of I is less than 81. So you are doing this. Whether A of I is less than 81? No, 81 is greater. So you have to increment the count for 81. Next, whether A of I is less than 92? No, 92 is greater. So you will increment the count for 92. Third time, whether A of I is less than 15? No, 35 is greater than 15. The count for 35 will get incremented. Next time, whether 35 is less than 41? No, 41 is greater. So the count for 41 will get increased. Now your j value, now the j for loop gets completed. The outer for loop, the value for I will get incremented. Now I value becomes 2, 81, 92, 15 and 41. This we will write as it is 68, 34. Now I is pointing to 81 and j is pointing to 92. So j will start operating from 3. In this iteration, j equal to 3, j equal to 4 and j equal to 5. So we'll start comparing whether 81 is less than 92. No, 92 is greater than 81. So we'll increment the count for 92. Next, whether 81 is less than 15. No, 81 is greater than 15. So we'll increment the count for 81. Next, whether 81 is less than 41. No, 81 is greater than 41. So we'll increment the count for 81. It becomes 4 now. J loop gets completed. Next, the I value get incremented. I becomes 3 now. So I is pointing to 3 here and j is pointing to this 15. So j equal to 4. So your j will operate from j equal to 4 and one more, j equal to 5. So we'll compare whether A of I is less than 15. No, A of I is greater than 15. So A of I is which one? Here. Whether A of I is less than 15, that is whether 92 is less than 15. No, 92 is greater than 15. So 92, the count for 92 will get increased. Whether 92 is less than 41. No, 92 is greater than 41. So the count for 92 gets incremented. The j loop gets completed. The I value gets incremented now. I becomes 4 and j value is pointing to 41. So j is 4. Only one comparison in the last iteration. So here compare here whether A of I is less than 41, whether 15 is less than 41. No, 41 is greater than 15. So the count for 41 will get incremented by 1. So now the j loop has also ended, and I also has ended, because we know that I is operating from 0 to n minus 2. 0 to n minus 2 is your I. So if I is operating from 0 to n minus 2, the minimum is 0, n minus 2, 6 minus 2, 4. So that is what we have seen, that I will only work up till 4. I equal to 0, I equal to 1, I equal to 2, I equal to 3, and I equal to 4. Fine. And j is operating from I plus 1 to n minus 1. So that is how we have seen that for each iteration j will be first time 1 to 5, second time 2 to 5, third time 3 to 5, fourth time 4 and 5, and the last one only one comparison is needed. You need to check what is the updated value for the count array. So we'll see what are the updated values for the count array. For 68 it is 3. Initially it was 2. For 35 the count is 1. For 81 it is 4. For 92 it is 5. For 15 it is 0. For 41 it is 2. Now you got the index values updated to these. So we'll just place it in the sorted form. The index values are 0, 1, 2, 3, 4, 5. So these index values, for 0 it is 15, for 1 it is 35, and for 2 it is 41. For 1 it is 35, for 2 it is 41, for 3 the element is 68, for 4 the element is 81, for the count 5 the element is 92. So the respective elements we have inserted into the indexed numbers. So now your sorted array is in this manner. So you have placed all the elements in the sorted form. That was because of this last statement in the pseudocode, wherein you are telling a of I, okay, for each of the element which you compared with the rest of the elements, whatever is the respective count in the index, you place the element for that index starting from 0 to n minus 1. So this is how the comparison count sorting works with respect to the time complexity. If you look into the time complexity of the algorithm, and if you see the comparisons that are done for this algorithm, it is same like that of the selection sort. So T of n, see, sometimes in the book C of n is given, which says the number of comparisons done. In few books you can see it is using the letter T to indicate the time complexity. So anyway, for the time complexity we are interested with the comparisons only. So either you can use the letter C of n or T of n, and in few of the books F of n is also used. T of n is equal to, with summation of I equal to 0 to n minus 2, and j is operating from where? I plus 1 to n minus 1, and there is one basic operation which is here. So now you simplify this summation I equal to 0 to n minus 2. The upper limit is n minus 1, n minus of I plus 1, and this one is there. Further simplification, I equal to 0, n minus 2, n minus 1 minus of I, open the bracket, plus into minus minus of 1 plus of 1. So this plus and plus 1 minus 1 will get cancelled. So you will be having summation of I equal to 0 to n minus 2, n minus 1 minus of I. So if you remember this is the same expression that you had got for the selection sort. Now substituting the value for I is starting from 0 to n minus 2. So each time you can start like this. First time n minus 1 minus of 0 plus n minus 1 minus of 1 plus n minus 1 minus of 2 plus. So like this you keep doing until you reach n minus 2. So that series is sum of n minus 1 natural numbers, which is given by n equal to n minus of 1 divided by 2. So further simplification, n square minus n divided by 2, which is equal to what? Theta of n square here. So the time complexity for this algorithm is given by this expression. So the time efficiency, as you have seen, it is same like that of the selection sort, because the key comparisons that are carried out here in this algorithm is same like that of the selection sort. But with respect to the space complexity, in selection sort we were using a variable min. This is a normal variable, but when it comes to comparison count sorting, we are using an array variable, and the number of locations needed for this array depends on the number of elements. So if more number of elements, then you are going to reserve that many locations for the count array. This is the only difference with respect to the space complexity. Otherwise, the time efficiency for the comparison count sorting algorithm is same as that of the selection sort algorithm. So this topic comes under the heading space and time trade-offs. Even the horsepull algorithm, which I have explained in my previous session, comes under the heading space and time trade-offs. So in computers, we have a trade-off between the space and time. If an algorithm is taking more time to complete its execution, it may require less space, and if an algorithm is taking more space to complete its execution, it may take less time. So this is what we call it as space and time trade-off. So these two topics, the comparison counting sort and the horsepull's algorithm, are included under the heading space and time trade-offs. Hope you find this session helpful. Please like, share and subscribe to my channel. Thank you. Bye bye and take care.